Let's move to Topic 2, Random Variable Part 1.
Before we can predict the behavior of any physical system, whether it's a packaging line or a microbial culture, we first have to categorize reality into one of two mathematical states. We do this by defining a random variable, a specific attribute or quantity whose value varies by chance from one unit of investigation to the next. The first category is the discrete random variable. These are isolated, distinct values you can count, with no fractions or decimals existing between them. If you are tallying the number of defective cans in a shipment, or counting individual bacteria colonies on a petri dish, you are working with discrete data. The second category is the continuous random variable. Instead of counting isolated objects, you are measuring data along an unbroken scale that can theoretically be divided into infinitely smaller fractional values. The exact pH of a sample, the precise weight of a cookie, the temperature at which milk spoils are all continuous variables. This table shows the structural difference between the two. For discrete variables, we assign probabilities to specific, isolated outcomes, and the total probability across all possible outcomes sums to exactly 1. Because continuous variables exist on an infinite scale, the probability of any single exact measurement is technically 0. Instead, we calculate continuous probabilities over intervals using a probability density function. Identifying whether your variable is counted or measured dictates the entire mathematical architecture you will use to analyze a process. Once we isolate a discrete variable, two absolute rules govern its probability distribution. The probability of any individual outcome must be 0 or greater, and the sum of all possible probabilities must equal exactly 1. Look at the highlighted graph from this slide. If we run a simple experiment, tossing 2 coins and counting how many land on heads, we map the discrete outcomes of 0, 1, or 2 directly to their specific probability levels on the y-axis. This table displays the exact same data numerically. We have a precise decimal probability assigned to each isolated count, 0.25, 0.50, and 0.25. To interpret this data mathematically, we calculate 3 summary measures: the expected value, or mean, the variance, and the standard deviation. By calculating the weighted average of all possible values, we find an expected mean of 1.0. Factoring in the squared deviations gives us a variance of 0.50, and taking the square root of that yields a standard deviation of 0.71. These summary measures establish the structural baseline required before you can apply specialized predictive models to complex real-world data. The most common specialized tool is the binomial distribution. It operates under 4 strict requirements: a fixed number of trials, independent events, a constant probability of success, and exactly 2 possible outcomes. In statistics, a success simply means the outcome you are tracking occurred. In quality control, detecting a defect, finding a trace allergen, or logging an accident is mathematically categorized as the success of the trial. This is the formula for binomial probability. It calculates the number of combinations for X successes in N total trials, multiplied by the probability of success, P, and the probability of failure. Applying this to a food packaging machine with a 5% defect rate, to find the odds of exactly 2 defects in 10 packages, we set our parameters. Running those through the formula yields 0.0747, or a 7.47% chance. This framework is universally applied across food science. You can swap the parameters to model microbial presence, binary consumer brand preference, or allergen detection. The math becomes more demanding when you need to calculate cumulative ranges. For example, finding the probability that more than 5 out of 15 participants respond positively to a new recipe. To solve this efficiently, we use the rule of complements. As you can see, we sum the probabilities for 0 through 5 successes to get 0.7158 and subtract that from 1, leaving a 28.42% chance of more than 5 positive responses. When your physical process evaluates rigid pass or fail outcomes, the binomial distribution dictates exactly how those outcomes scale. The binomial tool fails when an experiment has more than 2 potential outcomes. To solve for multiple variables, we use the multinomial distribution. This handles subjective categorizations, like plotting data across a 5-point sensory evaluation scale. assigning agricultural products to quality grades like A, B, or C, or conducting multi-allergen tests. Notice how the multinomial formula expands. The factorial notation in the denominator, along with the subsequent probability multipliers, stretches out to accommodate as many distinct categories of observation as your experiment generates. Consider a sensory evaluation where 5 trained panelists taste a new citrus juice. They categorize it into 3 options: too sour, just right, or too sweet. We map historical consumer probabilities against the exact breakdown of the panel's choices to execute the calculation. In this scenario, the formula reveals a 13.5% chance of observing that specific spread of ratings. The calculation structure remains identical whether mapping complex consumer snack ratings or testing a single product batch for multiple allergens simultaneously. The multinomial distribution allows quality assurance scientists to impose mathematical predictability onto highly subjective human sensory data. When you need to count the occurrences of an event over a continuous interval of time, space, or volume, the appropriate model is the Poisson distribution. The parameters for Poisson are specific. The data must be discrete, the interval must be fixed, the events must be independent of one another, and the overall probability of occurrence must be exceedingly low. This distribution also has a strict diagnostic check. For data to accurately fit a Poisson model, its expected mean, or lambda, must be approximately equal to its variance. This formula calculates the probability. It relies on lambda, the constant average rate of the event, and Euler's number, a mathematical constant approximately equal to 2.71828. We can apply this to microbial counts. If a milk sample averages 2.5 bacterial colonies per milliliter, we set lambda to 2.5 and our target x to 3. The formula gives us a 21.4% probability of finding exactly 3 colonies. In a factory setting, if a canning line averages 1 foreign particle per 1,000 cans, the Poisson model projects a 99.9% probability that any single random can pulled off the line is completely clear. Poisson calculates the odds of contamination when the specific events are unpredictable, but the system overall maintains a statistically constant failure rate. The models we have covered so far assume that the probability of an event remains constant across all trials. In small, finite batches, that assumption fails. To address this, we use the hypergeometric distribution. This model handles discrete data when we are dealing with a finite population and we are sampling without replacement. Because the total population is small, physically removing an item from the batch permanently alters the denominator. The mathematical probability shifts dynamically with every single draw. Imagine inspecting a box of 50 cans, where exactly 8 are dented. If you randomly pull 10 cans for inspection, you map the total population, the known defects, and the sample size through the formula to reveal a 32.16% chance of catching exactly 2 dents. For destructive food testing or auditing a finite batch, the hypergeometric distribution is mandatory because testing literally alters the reality of the remaining sample. The final discrete model approaches continuous manufacturing from a different angle, the geometric distribution. Instead of counting how many successes occur within a fixed sample size, this model calculates the exact number of consecutive trials required to hit your very first success. Unlike the shifting fractions of the hypergeometric model, geometric distribution assumes the underlying probability of success remains completely constant across every trial. If a bottling facility has a constant defect rate of 2%, we calculate the probability that the line will run cleanly for 4 bottles before producing a contaminated 5th bottle. The formula yields exactly a 1.85% chance. The geometric distribution models the physical time, effort, and material cost required before a systemic failure presents itself. The primary challenge in statistical analysis is accurately observing the physical constraints of an experiment and translating them to the correct mathematical architecture. Look at this decision matrix. The first diagnostic question is whether you are sampling without replacement. If you are drawing from a finite pool and the probability changes with every test, you are routed directly to the hypergeometric distribution. If the probability is constant, but you need to determine the exact number of trials until the first failure occurs, you use the geometric distribution. Mathematical modeling in the physical sciences relies on correctly matching the chaotic reality of production to these rigid frameworks, securing quality through absolute mathematical precision.
Thank you. Disclaimer. Artificial intelligence, AI, was used in the development of selected instructional materials in this lesson. The use of AI is intended to enhance clarity, visualization, and learning engagement, while all academic content has been reviewed and guided by the instructor.